Okay, we're going to start a new project today, and it's still going to be using a 8-pin or 8-bit processor. It's going to be a 12LF 1840. So the LF is low voltage, which is different than the usual. You're looking currently at a stepper motor that I put on the wall, and this project, I don't know if you can tell, but it's a clock, and it's set for, it's running twice as fast, or much faster than it normally would run, just because I've changed the amount of delay between each step or each time period. So instead of running once every minute roughly, it runs every 10 seconds. So it's about 9:10 right now. It's really a simple project. You could use the last tutorial and probably go from there and build this. So this is, what can I say about it? It's, it runs on 6 volts. I'll show you. It's only got a few pieces, which is about 16 minutes after 9 o'clock right there. But as you can see, it just runs over to really just one chip. There's not even a resistor or a driver on it because it's using such little power. Of course, it's using a 6-volt power source, which probably not the wisest idea. You'd need to have probably something plugged into the wall. And it's a really large lookup table. So all these steps are basically, I'm just telling it to go forward about 100 bytes maybe, or 100 bits, I should say. And it's programmed into each piece of data in a lookup table. I'm going to unplug it right now because, oops, it will eventually drive me nuts. But yeah, it's a clock. And it's quite simple. But our next project, which I'm just going to tip this down here, and I'll show you what it is. Our next project we're doing here will be this right here. Maybe turn it a little bit more and move a few things out of the way. Move this out of the way. But this right here will be our project. I just have to find where it is in the picture here. Maybe it needs a little bit more tilt. Okay, here we go. Will be what we're doing. And it's a very, very simple project. So that's the schematic right there. Obviously you see there's only a chip, an LED, not even a resistor, and 3.5 volts. And obviously you can see it working over here. That's the LED, it's a white LED. And the 12LF 1840, as it says right down there. And the program is very short, about 12 pieces of code, okay? And we're going to use the watchdog timer this time as well. And the watchdog timer is a very low-powered timer. And basically it will put the whole chip into a sleep state, and the watchdog timer will run for about 2 seconds, turn the processor back on, and then proceed to do a quick flash of the light or LED, and then go back into a sleep state. So the flash is actually 1/1000th of a second long. I don't know how I'm able to see a 1/1000th of a second flash on an LED, but that's what's been programmed into it. I checked it with my oscilloscope, and it really is 1/1000th of a second. And it's going to use roughly 25 milliamps for that length of time. And the sleep is about 2.2 seconds long each. And each sleep is roughly 500 nanoseconds or nanoamps. As you can see right there, that's 500 nanoamps, yeah. Well, it's 0.005 milliamps, but yeah. So let's have a look at this project here. I will just quickly switch things around here. Probably like that. That was not what I wanted to do. Let me just shrink this down here. New piece of software. So yeah, you kind of stuck with me goofing around with this. It's the OBS Studio down here. And someone mentioned it to me, and I thought it was a great idea. So that's why I'm using that right now. So I'm going to quickly explain a few things that we're doing using this data sheet. This is the data sheet for the processor we're using, which is the PIC 12LF 1840. Obviously, there's 382 pages. We do not need to know all 382 pages, nor do you want to read all 382 pages, but it's useful for some things. Obviously, not the stuff that we're using. I'm going to quickly go through and just show you a few of the things on this book here, or on this data sheet, and you might find interesting or related to our project. For instance, the low power feature. We're going to use the watchdog timer, as you can see right here. I could probably circle it with this tool right here, the watchdog timer. And it's going to be 300 nanoamps of power drained from the battery, which is so low. It's actually, this is going to be on, and what else is going to be on? There'll be some standby current on to, oops, there's a really bad circle. I'm not very good with this pen. It'll be about 500 nanoamps because we're actually at 3 volts. We're using 2 batteries and instead of 1.8 volts. So the 500 nanoamps is such a low amount of power that draining from these typical AA batteries, it'll take 500 years to drain that power. Obviously, the batteries will rust and decay and decompose way before that 500 years comes up, but I'm just telling you, it drains so little power on standby that you're obviously not going to have a problem with battery usage when we're doing this project. Where else are we going to go? Oh yeah, let's go down here a little bit. I just want to show you something. This is interesting. So there are 2 chips in this manual, the LF 1840 and the F 1840. The LF stands for low voltage. So this chip can only run up to about 3.5 or 4 volts of power, whereas the normal chips that we're using run up to maybe 6.5 volts. So it's good to know. So when I program it, as well as when I use it, I'm going to be using 2 batteries instead of 4. And also, obviously, it has it has 4,000 words of memory storage. That's quite a bit. That's yeah, we're using 10 on this example here. Boy, that is not a good circle. That's better. Okay. Let's go down a little bit farther and see what else we have. Okay, so here's your pinout of your chip. It's kind of fun scribbling on these things. Yeah, here's your chip, and that's the pinout. We're going to use the obviously 2 chips here. This one right here is your 3.6 volts. This one right here is your ground, and we're going to use pin 7 right here because we're actually going to put power out to an LED, and we're going to put it out through RA0, well, that string of letters, and that is port A bit 0. So when I start doing something on port A bit 0, that's exactly which pin on this chip will be activated with a high or a low in the I/O port. Where else are we going to go on this little cheat sheet of mine explaining where everything is? I'm going to run you down to, okay, let me just run down to number 20 here, and I'll show you the banks. Okay, so these chips work on banking. So when they have a lot of different registers to do different jobs, they will bank from bank 0 to bank 1, 2, 3, whichever bank is needed to get the job done. And obviously you can see this has several banks, and a lot of them aren't actually used for anything. They're pretty empty. Nonetheless, they do have a lot of banks, and we're actually going to use only the first few of them. We're going to run over to bank 3 and down to here and use this register right here, the analog select bit or byte for port A, and it's basically going to oh, did I change that? Okay, it's basically going to change the analog select byte over, or I'm going to change it by clearing it out to allow all of port A to be digital. And I'll show you how that's done, but that's on register C. Then I'm going to run over to bank 1 in this software, and I'm going to run down to this register here, tris A, and this is the port A register setup, or the port A input output setup. So I'm going to change port A, so it's going to be all output ports, or all output bits or pins. So every pin will be an output. And I do that by making them 0. A 0 on any bit represents an output. A 1 on any bit will represent an input. And I'm just going to clear the whole register so it all becomes output. Then I'm going to run over to bank 0. And I'll do most of my work here. Out of curiosity, register C as well is the I/O port on bank 0. So whenever you put a 1 or a 0 on that port, since I've made them all output ports, by the way, they will now have a high or a low put onto that pin, whether I put a 1 or a 0 onto those pins or that port address. So anyhow, we will now go over to a different part of this data sheet. And by the way, this data sheet is free. It's free download from Microchip. You just type out data sheet and pick 12 LF 1840, and then you can have this data sheet too for free. Let's go over to, I think I'm going to run over to page 41. Okay. Why did I go to page 41? No, I wanted page 61. Okay, yeah, I see that. You know you're getting old when you can't even see that, hey? Page 61. Okay, the oscillator, the clock on this chip does run at a variety of different speeds, because I'm going to use the internal oscillator, and it can run anywhere from, as you can see, from 31K or 31,000 hertz all the way up to, well, they say 32 megahertz. I think there's a mistake here actually. And just by changing this byte, the OSCON byte, the OSCON byte actually, we're actually not going to change it, but I'm just pointing this out. You can change the speed of your oscillator. We're currently just going to accept the default speed of 500 kilohertz, which is set that way by merely putting, obviously, those bits into this section of the byte, the OSCON byte. Actually, and maybe I'll just let me go back to page page 3. Let me go back to page 3 quickly. I just want to show you this. It wasn't page 3. It was actually page 20. Okay, here we go. So in page 20, you can see that the OSCON byte, oscillator control byte, is way down here on bank 1. Well, actually address or register 19, and I can change that byte in order to change the speed of the oscillator. Kind of interesting, eh? Let me run over to the next one, which is actually 89. Page 89 is right here. It's going to talk about a little bit about the power down sleep here. And so in power down sleep, there's a few ways to, well, it's one good way to put sleep is you type out the sleep instruction. So we're going to use the sleep instruction. And then there's another way to wake it up, and it's basically through the watchdog timer timing out. And that's the way we wake it up, is we're going to use the watchdog timer. Let's see what else is down here. There's a, you can read these things if you want, and they're actually, it's really good to probably read through a lot of these things. They talk about the low powered sleep, and you can wake it up with a variety of different things, including the peripherals or whatever. And I wanted to point out something kind of important here. What was it? Oh, I think it's on page 93. More information on the watchdog timer, how it works, watchdog timer modes, and how that works. You may not need that. This is information on the watchdog timer, and we're actually using the watchdog timer as it is in reset value. So when it starts up, every part of your, all of your registers, all of your options and accessories are all set up a certain way. For instance, you see these little numbers up here where my, well, where my blue pen's about to circle, like this. All these little numbers here, they represent the power on state of this register. So you can see in the power on state, there's like a, this register will be 0, or this bit will be 0, and this will be a 1, and this will be a 1, and this will be a 0. What you'll notice is the power on state for the watchdog timer control, the reset value, as they call it, will be set for about 2 seconds, and that's what we want. We want a 2-second watchdog timer, so that means that I will put the chip into a sleep mode for 2 seconds with the watchdog timer, and that's roughly the way it's been set up right there. You can see that 0, 1, 0, 1, 1 right here, right there. Where is that? Right here, between bit 1 and bit 5. This one, this one, this one, this one, and that one. 0, 1, 0, 1, 1. There you go. Down there. But yeah, if you want to change that, if you want to have, instead of a 2-second sleep, you want to change it to maybe a 4-second sleep, you could change that over to 1, 0, 1, 1, 0, 0. And then you get a 4-second sleep, all the way up to even 256 seconds, or all the way down to even 1 millisecond. You can just change these bits right here to do that. Not that it's of any value to most people, but it's always good to kind of play around with these things so you kind of know how your chip works, if you'll enjoy that sort of thing. I'm going to just zip down to, actually, yeah, so that's how the sleep would work. But if you ever want, I'm just going down to, I think, 89, right about. No, I'm going down to 95. No, I'm going to go down to, what do I want to explain to you next? Oh, maybe the, I think I'll explain the instruction set again briefly. So I'm just going to type in something here, 309 probably. Okay, so here's your instruction set, and we're going to use a variety of these. Again, let me highlight the ones I want to use. So there's only a few instructions, very limited number of instructions for this project, but we're going to basically clear a file register. That one right there is going to be used, that instruction. And maybe we'll, yeah, we'll have a little tiny timer for delay for that. The light actually is going to come on for 1/1000th of a second, but that'll be a quick little delay. And oh yeah, we're going to use both of these right here. We're going to set and clear a bit. Basically, that pin will go on and off with these two instructions to turn on and off that LED. Do we have anything down this section? Oh, a literal. Okay. Maybe we're going to move a literal into the banking register, right? So that's how we move from our one bank to the next. We'll use that one. And we'll move a literal into the working register. That one right there. And I think we will just go down to the next. Yeah, there's 49 instructions, so obviously not a lot. We're going to use the go-to statement here. And I think we will use the sleep one right here. Fantastic. Yeah, so that's all the instructions we're going to use. And as I said, there are 14-bit instruction, very small. Where else are we going to go with this, what I want to explain here? So I'm just going to run down to page 321, 321, right down here. The electrical specifications. Okay, so these here chips all have specifications on how they run. So what does this say here? Oops. This says advanced information. Okay, that's nice. This here chip runs between, well, I guess it depends on which one it is, right? Okay, so 25 milliamps is what the max is amount of amperage you can sync or source on an I/O pin. So we're going to be probably since we don't have a resistor on that LED, it's going to try and draw all 35 milliamps out of there at 3 volts roughly. So that's, and so the specifications go through a whole bunch of stuff down here. For instance, by the way, this obviously is for the non-low voltage chip. It's the 12F1840, and this information is for the 12LF1840. So you can see down here, since we're using the LF, at about this level, you can get up to 24 megahertz if you want, up to between 2.5 volts and 3.6 volts. Whereas you can't really get a 32 megahertz frequency on the chip if you're below 2.5 volts. And that's just, if you know how to read these things, it's kind of handy. And they just tell you a whole bunch of weird things. This tells you how much it wanders in frequency, actually. The chip, when it's based on temperature. So this says it wanders plus or minus 2% based on this temperature range here. Kind of interesting, eh? Yeah, and it's tons and tons of information going down here. It tells you all about the voltages and how much power is being used for everything. But where else I want to go with this next bit of conversation here? I think that is as much as I needed to tell you about all of this stuff here. Okay, so let's go over to a MP Lab. So we're going to start this, and by the way, again, I'm using MP Lab 5.20. I got it from the archive section. It's free from Microchip, and Microchip is also the people that build these little computer chips here. So if you're into this sort of thing, the chips are really cheap. They're maybe a buck a piece, something like that. I don't know. Anyhow, if you're actually interested in these chips, for the first 3 people that will email me, you can see my email address right there. First 3 people that email me their home address and their, I guess their YouTube username, I will send them a couple of these little chips we're using right now. It's the 12LF1840, and I'll just mail them to you. It's free of charge, just a merch, I guess, if you want to call it that. But anyhow, this is the starting page right here of the MP Lab version 5.2, and we're just going to build our program now. So right here, I click on this little yellow thing, and I go over to a standalone project, and I say next, and then we're going to use, the device will be a 12. By the way, I'm just using a Windows 10 based computer. And I'm going to program an 1840 something. Yeah, right there it is. So there's that 1840. Next. And I don't need a support header or debugger. By the way, I'm using a PicKit 4 programmer. You could use a 3. It makes no difference. The 3 actually I like better. There you go. And there's only, we're using assembler, so that's it right there, or assembly language, and that's it right there. You could use C. It's a language I never picked up much. I did some programming with C, but it wasn't really my favorite language of choice. This one's very easy to remember and use again and again. I sometimes go for 6 months at a time, maybe even a year between projects, and I find it very easy to remember this language. Anyhow, I'm going to call this project test 17 and finish. And then I will go over here to my file folders, and in the source I'll go left and then a right click and then a new simple, and I'm going to call it test 17 because I'm not that creative at this point. Great. Okay, so that's my program. Oh, I don't need this junk here. Get rid of it. So first thing you do with these programs is you pretty much always have to set up the chip itself. So the compiler, or actually the assembler, is going to actually want to know how to put your chip together, or exactly what you want it to do in the way it runs, such as whether you want a watchdog timer or not, or whether you want your chip to have an external oscillator or not, even if you want to lock up your code or not. So in production here, you click on that, you go down to set configuration bits. So we're going to set up our configuration bits to do a few things. I want an internal oscillator, by the way. So I go down here, I set this one for internal oscillator. And like I said, set for 500 kilohertz in the startup stage. If you want, you can change that to whatever range you want once you're inside your program. But you can't change the speed right here. You can just initiate it as an internal oscillator or external. By the way, there's external right here, and I can have an external low-powered one that runs at certain speeds between 0 and 500 kilohertz, or as fast as up to 32 megahertz external, by the way. Down here, actually, just out of curiosity, these are those were actually not crystals. Those speeds are based on running a clock speed in. If you want to run an oscillator, a crystal oscillator, you would set it up here. Obviously high speed, that's good for up to 32 megahertz. The really slow one way down here, it's good for actually, where is my screen here? Yeah, you can see, and by the way, they use up 2 pins, right? And you probably don't want to really use up 2 pins on a very small chip. Actually, they do have a setup here for a RC oscillator. You can take a resistor and a capacitor and put it on the pin, one of the pins, and it will work as your oscillator. Currently, we're heading for just internal oscillator, so all the pins are going to be used for I/O, or input-output. Watchdog timer we're going to keep on because we're going to use that. We don't need a lot of these other things. I'm going to just turn off these things here. Brownout, no thank you. Just turn off a few of these little things. Was there something else I want to turn on here? No, I didn't want the phase lock loop on. You do turn that on when you're using the high speed oscillators, but we don't need that. Low voltage programming, I'm going to leave on because that's what we're going to do. We're going to do some low voltage programming of this chip. Normally we don't have that on, but this time we do. So internal oscillator, watchdog timer, and low voltage programming. Okay, so now we're going to generate some source code by clicking on here, and we're going to copy and paste all this content right here. Copy. And let's just get this window cleared and paste what we just did right there into this section here. Okay, so I know it's a lot of non-data programming at this point. We're not really coding anything. We're just setting up our chip. And what I want to do right here is tell the compiler where I want my coding, or my code, to go. And I want to start obviously at the very beginning of the memory bank, because that's exactly where I want the stuff to all go, so I can keep it all at the bottom of the program memory. Okay, so what we're going to do here is we're going to start building our code right here. And let's go back to there. No, I actually don't want to go back to there, because I was going to use that as where my labels are going to go. So I'm going to write a little bit of code here, and then we'll talk about it, okay? And then it will make sense to you. Okay, I think that's as far as I want to go right now. So what I've done here is I've written out my first 5 instructions. And the first one, move literal into the banking register. So I'm shifting over to bank 3. Remember at the very beginning of my conversation, I was saying, oh, bank 3 has some stuff we want to change. Well, we're going to jump over to bank 3 by using this instruction, move literal into bank 03. So I'm moving a 3 into the banking register, and now we've just gone to register bank 3, and we're going to clear file register OC. And OC was the register that cleared the analog select byte. Well, cleared it all down to 0, which made it all digital. So all your ports, or your one port, actually port A, will all be digital. Now, what you'll notice is that C is pink. That just means there's a problem because this here has to be defined as a hexadecimal number. And the way you do that is you add a OX or 0x at the beginning, and then it's defined as a hexadecimal number. Normally, it's not a problem if it's all numbers, but when you get alphanumeric numbers, and that's an alpha number, alpha number, that's an alphanumeric number when you have an alphabet in there, and it seems to have problems with that. So you designate it as a hexadecimal number with the OX. It clears that. Matter of fact, I'll do that one right down here as well with a 0x. It solves that problem. I mean, I could have done that with this one too. I could have typed in OX. I don't know why I don't. I just leave it that way. Anyhow, so I've just cleared out register 0C. So now, and actually if you wanted to, if I was to say, oh, let's clear file register, that would be just as good because that's the mnemonic for that register. That register is called ANSEL or ANSEL, or more accurately, analog select byte. But I usually try and keep consistent for the people who are learning, and that is what I do. I keep everything with a numeric address instead of an mnemonic address, so people can look and say, oh yeah, I see what you're talking about, instead of the idea of having some numbers and some words intermixed along this here instruction set. So if you are used to maybe putting mnemonics in with your instructions, you go right ahead. So anyhow, now we've banked over with move literal into banking register, at 01 actually into banking register. It will now go over to bank 1 because of this instruction here. And then I will clear file register OC over here. And OC in bank 1 happens to be your I/O port setup. And it's a TRIS register is what they call it, TRIS. And I could have called it, again, a mnemonic of TRISA. And that would be good enough because that's the mnemonic for this address. But anyhow, like I say, I'm just using this format here. So I've just cleared it, which made every bit in that byte go to a 0. Obviously, when you clear it out, everything goes to 0, and zeros represent outputs. If I had put a 1 on any of the bits, it would have been assumed to be an input at that point, or you define that port as an input. So now I've defined my ports as all output ports, actually output bits more accurately. It's one port, port A. Anyhow, they're all defined as output. Now I've run over now to bank 0 with that statement. Move literal into banking register 0. Okay. Now, so I've defined my ports. And by the way, you know, guys, sometimes if you like to keep notes, you can keep notes here. You just throw a semicolon down. You can type out whatever you want. Define I/O ports as output. There you go. You can just write down instructions all the way through here, or points that only you will actually see. The processor or the assembler will, or compiler will never see all this stuff. And I'm not going to put this here because I keep it nice and simple for everybody to look at the code as simple as possible. Now I'm just going to write a bit more code here. And again, this is really one of the most basic programs you can build because, like I said, it's going to be less than a dozen lines. Oops, I need my glasses on. Give me a sec. Okay, here we go. Okay, so bit set file register. Okay, so normally, so I'm actually setting bit 0 on file register 0C. Actually, let me just make this a 0 and an X to define it as hexadecimal. So 0C is my output port, and or yeah, it's my port actually. So 0C is my port, and I've just written to bit 0 as setting it. So I've just set bit 0 of that file register OC to high. So it's going to go high. There's going to be a 1 or a high, or whatever you want to call it, or 5 volts, it's up to you, on that pin. So that's going to turn the light on, basically. Bit set file register OC bit 0. Okay? So now I've just turned the LED on, right there. And now I'm going to delay that light. I don't want to keep it on for a little while, actually 1 millisecond, right? So since I'm running at 500 kilohertz, my delay will have to be rather short. So give me a second here. Let me just do a little typing. Let's not use that. Let's try a move a literal into a working register. About 28 hexadecimal. See, I didn't have to actually put an OX in front of that because it didn't seem to complain because I had no alphanumeric on it. I'm going to use a register, just any old register. I chose 22 today. I could have used anything from 20 to about 40, I think. Can't remember how many are in this bank. Okay, yeah. So that's, there's a delay right there somewhere. Decrement a file and skip if it's 0. Register 22. And there's that go to statement. I think that's pretty good. Okay, I will stop right there. Okay, so what I've done here, that's just a label. And that's just a label right there. Those labels are in reference, so you can go back to it using like go to statements and that sort of thing. Actually, I didn't really need a label there. Maybe I'll get rid of that. Yeah, I will. Does not matter. So down here, I've just turned on the LED. I've set bit set file register on file register OC bit 0. I've just turned it on. I've moved a literal then into a working register. A working register is just because we have such a limited, it's a RISC processor, a reduced instruction set processor. So we have very few instructions, only 48. So just to haul a number into a register, you usually have to put it into a working register first, and then from there you transfer it into the file register. So I'm moving 28 into the working register with this command, and then this command down here, move the working register into file register 22. That's how we got a number into a file register. We had to go through a working register to a file register. And then down here, that's just a label. It doesn't really look at it right there. But then at this point, I am now going to decrement this file register 22 all the way down to 0. And that's going to be my delay. So decrement file register and skip if 0. What that command does is it decrements this file register, and the 1 merely means it's going to toss the answer back into file register 22. So since register 22 actually has the value of 28 inside of it, because I've entered it in up here, right? I put 28 into file register 22. It's now going to decrement it by 1 and put it back into itself. So it's going to take register 22, which is valued at 28, and make it into a 27. And then go down to the next line down here, because it would skip over this line. Actually, it would skip over this line right here if the value was 0. But it's not 0. It's actually 27 now. And this instruction says go to delay, which is spelled wrong, and go back up to here. I could have spelled it right. And then it'll go up here, and then it'll read this instruction here, and it'll say decrement it again, and then go back up, decrement it again, go back up. Eventually it's going to go down to 0. When it finally hits 0, it will skip over top of this instruction and fall out of this loop, because decrement file skip if 0, that's what the command will do. And when it finally jumps out of here after going through, I'd like to say 28 loops, it's actually 40, because this is hexadecimal and we don't count hexadecimal like we count decimal. So this is actually equal to 40. Remember, hexadecimal has everything from 0 through to 9 in its number system, as well as A, B, C, D, E, F. And that's why 28 is equal to 40 in hexadecimal. So anyhow, it's going to run through 40 loops and drop down to the next command, which will be to turn the LED off. Bit clear file register. Oops, that's all right. So it's now going to bit clear file register OC, which is my IO port, bit 0, which was actually pin, was it pin 7? 1, 2, 3. Yeah, it's pin 7 actually is what's being cleared now. So I've just turned off the LED. So this span of time here is actually 1 millisecond. When the chip is running at 500 kilohertz of speed. So what are we going to do? Okay, yeah, now at this point, after that, I put my chip to sleep. I've just turned my LED off, and I'm going to wait for 2.2 seconds. So the chip goes to sleep. I'm done. That's it. And end is something you always have to put an end statement down here for the compiler so it knows it's finished the program. That's the whole program right here. How many instructions is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. And realistically, the funny thing is, I could actually have gotten rid of this one right here. These two. The reason being is this, these processors actually run fine without having the analog select bit cleared to digital. It runs fine as long as you do not actually want to do any input. I just set this up with this included in case somebody wants to use this program and modify it so you can use it as an input port as well. It's just for your convenience that I've set it up that way. It's not even necessary, but it is there. Anyhow, I think it's ready to run. So we're going to put this instruction or this program into the chip. So what I'm going to do is I'm going to put this chip, maybe I'll flick over to the camera here. I'm going to put this chip into my programmer, and we will program this thing. So this goes in here like so. Yeah, so this half is actually just the programmer. That's the PIC kit 4, and these are all wired in from the PIC kit 4 into this little breadboard, which is glued onto my PIC kit 4. This is totally unrelated. But anyhow, That's the chip. And let me just go back to what we're doing here. So I'm going to go up to here, and I'm going to click on the little hammer to program that chip. And it's programming it right now, and it says, hey, the build was successful. I'm going to put it into the chip that is on my USB port for my PIC Kit 4, that little chip sitting on that blue thing. And it's going to do that, and eventually, oh, yeah. So what I got to do here, actually, I should check, see if I have, go over here to File, run down to Properties, Test 17 right here. Go over here. I know it's kind of fiddly. Go over here, I'm sorry, to PIC Kit 4. And then go over to Memories to Program. Change that to Power. Okay, so I have to let this thing know that I'm actually wanting to have 3.25 volts put on that chip from the USB port so that it can program it. You need voltage on that chip to program it. Apply and change. So that's why the connection failed there. Now I'm just going to send it through again. It will work this time. Build successful. Connecting to a programmer. Are you aware that you have a low powered thing? Yes, I am. And go for it. So it's going to program it. And da, 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 da. So there you go. Oops. Well, that's nice. So it's programmed, and I'm going to now just take it out of there and put it into my project here. Not that it wasn't working before, but sometimes it's always nice to see. Well, let me disconnect a wire before I put this in, because sometimes it's kind of nice not to blow things up. And that goes in there. This goes in here, and look at that. Nice and bright and flashing. Like I say, this will last for 20 years on these batteries, just because it uses such little power. Normally, if you had the other programming that I'd done in the past, it would probably last for maybe a week. You know, I mean, they're pretty good chips, but this 20-year life cycle is pretty amazing. Anyhow, that's done. I think that is everything for this project and this tutorial. Enjoy, guys. Take care.